Okay, cool. Let's get started. Cool. Yeah, so today we'll do GPU programming, and I posted the outline for the project proposal. So there's an outline for the write-up and there's an outline for the presentation. So if you have questions, just let me know. Please sign up. There's a sign up sheet somewhere. There's a link somewhere online. You should post your groups and we'll make the schedule at some point between now and the presentation time. Yeah, and the homework is due next Tuesday, I think, the MPI one. Cool. Questions? Are we good? Okay, so yeah, so far in this class, we have been here doing CPU computing. So for GPU computing, it's called heterogeneous computing, which means that there is a host, which is like usually the CPU and all the things that are associated with it. So the stuff that we have been working on before, like host memory and caches and so on. And then there's this introduction of this device, which is this alternative computing resource that is attached to the host, and it has its own separate like threads and computation and also separate memory. So you write code for both the host and the device. Yeah, and so far today we'll be focusing on how to write code on the device. So usually the way it works when you write CPU code, so you have this total application here, and then yeah, there's blue and green, and the blue code runs on the CPU and the green code runs on the GPU. So you have this application and not all of it runs on the CPU or the GPU. Usually you offload some part of it onto the GPU and you specify that just in your program. And the entire application is the combination of both GPU and CPU. And the GPU is not like a general purpose interface. It can only do some limited form of computation. So you still need the CPU to do some basic functionalities. Okay, so usually when you write GPU code, there's a simple 3-step flow that you follow. The first step is, so this is the CPU, this is where we were before. Like you can parallelize this with OpenMP or whatever we were doing. And it has some connection called PCIe, or more recently there's NVLink, which is a faster connection. And this is just the memory connection between the CPU and the GPU. And this side is the GPU, and this is what it looks like. It has its own threads, it has its own DRAM, L2, and so on. And the first step is that you get some input data from the CPU. So you either generate it in the CPU or you can do like disk IO, you can read your data, and then you have to copy it through the connection to the GPU onto the GPU. And then after that, then you load your GPU program onto the GPU. So here you wrote some code in CUDA, and then you load it here, and then you execute it onto the GPU using the architecture that's already available, like the cache hierarchy and the threads. And then after you're done, the results are in GPU memory, so you have to copy them back onto the CPU for post-processing. And usually, maybe there's something else that you want to do here, like you can write it to CPU disk, you can do visualization. You might have multiple rounds of this 3 steps. Like if your application has several parts that would benefit from being offloaded onto GPU, then you would just repeat this multiple times. Okay, so let's get into how you do it. So CUDA stands for Compute Unified Device Architecture, and it's a way of exposing GPU parallelism using general purpose computing. And basically, the high-level idea is that GPUs are based on massive parallelism, so you want to expose as many threads as possible in CUDA. And it has a lot of language bindings, like you can do it in Python, you can do it in MATLAB. The one that we're going to do in this class is C++, because we do C++ and everything else. Yeah, and it's just these extensions that you can use to do heterogeneous programming to offload your code onto the GPU. And it has APIs similar to regular C++ to manage devices and the memory and so on. Okay, so we'll start with a really easy example of vector addition. So like I said, GPU computing is about exposing massive parallelism. And vector addition is embarrassingly parallel. And more recently, some people call it pleasingly parallel, which means that everything is independent and nothing is interacting with each other. So vector addition just means like you're adding the elements in the vector. You're adding the vectors element-wise. So everything is completely separate and you don't need to do any synchronization or dependencies or any fancy algorithms. So you specify your GPU kernel, just like writing it with the C++ bindings. To say something is going to run on the GPU, you just put this global with underscores in the front. And this, my kernel, is like your function name, but it could be anything. And in this example, the parameters are void, but they could also be anything else. So like you would just pass in arguments just like a regular C function. So global means that you run the thing on the device. And this is like step 2 in what I was showing you earlier. After you've offloaded your data onto the GPU, then you're gonna you run this code that's written in CUDA. And you call this from the host code. Yeah, so you write it in the host code, but like then it gets offloaded onto the device. And the compiler is called NVCC, which separates your source into host and device. And yeah, so the device functions are going to get processed by the NVIDIA part, and the host functions like main and any other host functions you write get processed by your regular host compiler like GCC. And the compilation happens in multiple steps. So like the NVIDIA part gets compiled separately from the main part. And when you call your function, you have to give it these triple angle bracket syntax. So this is different from C. In C, you would just call like my kernel with these parens, but you have to give it this run configuration in CUDA. So the run configuration is there's two things that you have to pass in, and then there's some optional parameters. The two things that you have to pass is the number of blocks, which is in some sense the number of some notion of parallelism. And then you also have to pass in this threads per block, which is a finer grained level of parallelism. And the maximum threads per block you can pass in is 1024. But for good utilization, you want threads per block, usually at least like 256 or something like that. It doesn't have to be exactly 1024, but it should be a close constant factor to 1024 for good performance. And this thing can be, it doesn't have to be determined at compile time. You could find num blocks at runtime. But one common paradigm that you write is like you fix threads per block, pretend it's 256, and then your num blocks is like your input size. So it'd be like n. So num blocks would be n divided by threads per block rounded up. Okay. And these triple angle brackets are how you call the device code. This is your kernel launch configuration. And the parameters are this configuration that you pass in, which is usually dependent on your problem size. And that's all you need to call the function on GPU. Like I said, the host and the device side have two separate memories. So you can specify pointers both in host and GPU memory, but the pointers are separate. So like pointers are just addresses, and both of them have separate address space. So you can pass in the pointers and it won't complain, but it will be wrong because like if you pass in host pointers into the device part, then that's pointing to something in host memory, which the device doesn't really have knowledge of and doesn't have memory on, or doesn't have meaning on the device, and then reverse for the host. And so one common way to do this, and I'll do an example later, is you have some host memory like you normally would. You just have like an array in C++, and you could call malloc to make your array. And to get memory for handling that array, like you want to copy it onto the device, you would also use like CUDA malloc, CUDA free, and CUDA memcopy, which are just the same API as regular malloc free memcopy, but just with this CUDA in front. Yeah, so usually the way it works is that you make some data either through malloc or through stack allocation in host memory, and then you use CUDA malloc to make a similar allocation on device memory, and then copy the memory from host to device. So to expose parallelism, if you want to run parallelism on the device, you have to change this angle brackets. So if you, the most basic configuration, you can write 1-1, which is one block and one thread. And this will run your program. Like this will finish, but the performance will be quite bad because ideally you want larger numbers in here, both for threads and blocks. And so first we can make, ignoring threads for 1 second, we can make blocks into n, which is the vector length, which is your problem size. And so we're going to do vector add, and this would, instead of executing this add function once, we would execute it n times in parallel. And this is how you would write the add function in CUDA. So you would pass in your 3 pointers to arrays A, B, and C, where they are ints. And there's some global variable that you don't have to define yourself. But It's called, yeah, there's block IDX and later there'll be thread IDX, which are global variables like C++ style. These are zero index things that give you indexes into what block you are. So this is kind of like MPI in that like you write one program, but everybody runs the same thing separately. But in MPI, like we had ranks, and this is kind of like ranks, but instead it's called blocks. So blocks are just your index in your total space. And this is how you tell where you are and which part of the computation you should do. So you use your block index, and this is just because we specified blocks to be up to n, then this would go 0 through n, and these would run in parallel in blocks. And then you use it to index into your array, and every block would handle a different element in the array, and then at the end, C would have all of the correct vector addition. These are, like I said, these are built-in variables, and the range comes from the kernel configuration.
I'm a bit confused. Where is the like the block numbers?
You passed it in here.
Okay, and then but like this method add,
Mhm.
is that like the add method is being run like per or it's being run like per block, but like is it like where is that like in relation to like this?
What do you mean, where's the, oh, like this is how you would call it, and then add, you would define it like elsewhere.
You define it.
Yeah, like you would imagine like in C++, you would have a main, and then this would be like at the, like just how you write another function that you would call from main in C++.
Yeah, but you don't like define it with the triple brackets, you call it.
Yes, yeah, exactly. You don't define it with the triple brackets. You just call it with the triple brackets. So that is important because often the triple brackets are not known until runtime. So you can't really call it, or you can't define it with triple brackets. Yeah, good. Does that make sense? Yes.
So like follow-up question, like, is X a member variable of block index? And if so, what does it refer to, and what are other member variables of block index?
Good, yeah. So X is a member variable of block index. Block index also can have Y and Z dimensions, because right now we're just doing it in 1D because this is an array. But if you wanted to do in 2D, you could actually specify the block to be like a 2D grid. And so you would have X and Y dimensions. And you can also do for 3D, but I think it just goes up to 3D. Good. Does that make sense so far? Okay, so this is how you would call it. Like I said, you first allocate these host pointers, which are just regular C++. Or I guess this is even just regular C. And then you would allocate these device pointers, which just look exactly like the host pointers, but here they're just called d sub a for device. And the size is just n, which is here a constant, but you could also pass it in at runtime, times size of int, which is like this is the system size in bytes, because you need the size in bytes to pass into malloc. And so, yeah, so you call CUDA malloc, which takes this API, very similar to CMalloc. You pass in the pointer that you want to instantiate, and you pass in the size in bytes that you want. And so you allocate the space on the device using CUDA malloc. And then this is how you would malloc just your host side memory. You would just call malloc with size. So the API is a tiny bit different. In CUDA, you pass in the pointer as one of the arguments, but in C, you assign it onto the pointer, but it's basically the same idea. And then the random ints is just like generate the input. So it's not included in this code, but it's basically just calling rand on every single element. So yeah, so like I said, you have to allocate the space both in device side and in host side. And then you copy your input. So the input was in A and B. And so you just do mem copy. This is dest, source, size, and a direction. So that the direction is different than in C. In regular mem copy in C, it'd just be dest, source, size. But you can pass in this argument, which is the direction. Here is host to device. So it's passing in the direction in which you want to transfer the data. And there's other options, like you can do device to host and so on. And you can actually, like you could pass in, I think there's like memcopy default. So you don't actually need to pass in either host to device or device to host. But this is one extra level of checking just to make sure, like if you get your, like if you got your pointer order wrong, but you got your string right, then it would complain. There's just another check at compile time. But if you passed in default, it wouldn't complain whichever direction you passed it in. And then you would call add. At runtime, you pass in the number of blocks, which is n, your input size, and 1 here is the number of threads. And these are the device pointers. So d sub a, d sub b, d sub c. And then you would, after add is finished, then you call memcopy. The answer is in d sub c. So now c is dest. And d sub c is source. Size is the same. And then now this is device to host. So it's in the opposite direction. And then after that, you just clean up with free. Make sense?
Can you only call like one CUDA function at a time? Like could I have like multiple functions for I do the copy back from the device to host?
Like here, could you call another CUDA function?
Yeah.
I think so. Yeah, because like d sub c is still, as long as you don't overwrite the output, I think it's okay. But is there a reason to call another CUDA function between here and memcopy?
No.
Okay. Yeah, I think it's correct. Yeah, I think it's technically correct. Maybe it would be better to copy it out because this would still take up room on your device. So like to use as much as possible for your next function, you probably want to clear it up as early as possible, but I think it's not wrong to do so.
But should we do some synchronization between CPU and GPU? Because maybe we encountered that the company is not finished yet. At this time, we copied those some finished value to the host pointer.
Yeah, there is some call, not pictured here, but it's like CUDA synchronize. In the handout that we will give in the homework, it's automatically already there, but you would call that after your device.
Wait, sorry, what synchronization do you need in this example?
There's just like a global synchronization to tell the host that you're done with the device.
Oh,
Yeah. So that's just like some standard function. It has nothing to do with the algorithm.
Yeah.
It's just kind of like, it's like MPI finalized, like it's just, we're finished with the whole thing. Okay. Yeah, so right now we parallelized over the blocks, but you can split the blocks in even more fine grained, so you can split them into parallel threads. And so if you use the parallel threads rather than the blocks to do the add, you would instead use thread IDX instead of block IDX, and thread IDX also has X, Y, and Z dimensions. So you can make thread blocks also in 2 dimensions or 3. Yeah, so you would do this in thread IDX, and then in main, instead of calling n as your block, you would call n as your number of threads per block. So this is 1 block with n threads. And here, n was 512 in the example, so it can work, but the max here is 1024.
I'm still not understanding much about thread index. So like, for example, like let's say we had a problem where not each thread or each block, whatever, gets an equal amount of like input data, right? It's not as equally divided. So some block might have a couple more data or more data, and the other one might have less. So in that case, would .x return different results in per block there?
Sorry, can you say it again?
So like, let's say I had one block that had, I don't know, 4 pieces of data, and another one had 3. And in that case, when I'm using thread index.x, or I guess thread block.x there, that would be 4 and 3. Would those return separate results, or would it be the same? I'm confused about what the variable thread index is in CPU.
The thread index, yeah, okay. So the thread index it's independent of the algorithm. So like you can note that add like right now, because this example is really easy, like everybody just has one variable, but if everybody had to do variable amounts of work, thread index is just something in the hardware defined across however much you gave it in the launch configuration. So like how the mapping goes from thread index to your actual algorithm is defined by this function. There's no like inherent division of thread index versus the actual work. Does that make sense?
And could you elaborate on the difference between threads and blocks?
Yeah, I will talk more about it later,
Okay.
but threads are more fine-grained than blocks, and there's additional benefits that you would get using threads over blocks. But I'll talk about it very briefly, and then maybe you can ask me again at the end if I didn't answer the question. Thank you. Yeah, so this is one really traditional indexing method that you do in CUDA. So you have blocks and you have threads, and you have some fixed number of threads per block. And so often you want to get some globally unique ID within your overall space. Often, like in this example, you want to index into a 1D array. So the way you would do this is kind of like indexing into like a matrix in row major that we just did previously. So this example, if you have 8 threads per block, which is similar to like your row in your matrix, then you would index, like thread index is your column, block index is your row, and then M is your row length. So this is one really common thing that you would do all the time to get a unique index into your array or into your like overall work. Okay, so this is just an example. Let's say we wanted to operate onto this thing, and if our block size in terms of number of threads is 8, so the block would be 2, because this is 0 index, 0, 1, and 2, and then the thread index inside of it is 5, again 0 indexed, and so yeah, so you get this like using this unique indexing. And these are built in, so block IDX, thread IDX, and also block dim is the number of threads in the block. So that's another global variable, or you could define it like outside is just like a, at the top of your C++, you define like hashtag number of threads is whatever it is, and then you could use that also. And then if you combined both threads and blocks to use your add, or in add, then you would have to use this global indexing to find your global index into your vector.
What would be blockdim.y? Like, is there a variable blockdim.y?
Yeah, here, blockdim.y would just be 1 because we haven't specified the block to be 2 dimensions. But if you do specify your grid to be 2 dimensions, then blockdim.y can be something arbitrary, and you can set that. Okay. So yeah, so if we did it with blocks versus blocks and threads, now here n is much bigger than we had before. Before it was 512, and threads per block is some constant. And this is just the same as before. So host pointers and device pointers, and you malloc your, malloc your device memory, you malloc your host memory, and then you copy A and B again. And this is the only part that is changed pretty much. So like I said, this is a common pattern. You have n, which is your input size, you have threads per block, and your number of blocks is input size divided by threads per block is the number of blocks that you get. And then after that is the same, you just copy the result out and then you free it. Usually your problem is not a friendly multiple of your block dim. So to avoid accessing out of your bounds, then you would have to check that you're not going past the end. And you would do your work only if your thread is some valid thing that can access your array. Yeah, and then you would have to update this launch. This is just rounding up. So why are we doing threads? They seem unnecessary because we already had blocks. And if you had enough blocks, then you would be totally fine. And then but you have to do this complicated indexing. And the difference is that unlike blocks, threads can synchronize within your block, and they can also do communication within your block through shared memory, which is a faster memory than. So I'll get to it later, but there's 2 levels of memory on your GPU. One is faster, that's shared memory, and one is slower, that's global memory. And threads in the same block can synchronize through shared memory, or they can communicate through shared memory. Okay. So we can do an example about how you would use shared memory. Suppose that we have a slightly more complicated example algorithm we want to do, which is 1D stencil. And 1D stencil is just, instead of doing like element-wise addition, now every element of the output is the sum of some neighboring elements from the input. So if this was your output ID, then you would sum up these elements from your input. So you would sum up like 7 elements from the input to get 1 element from the output. So your output is slightly smaller than your input. It's like, in this example, it'd be 6 smaller, like 3 on the ends, but it's pretty much the same size. Yeah. Does the problem make sense? Stencil is like a really common paradigm in scientific computing. You can get way more complicated stencils in higher dimensions, and bigger also. Like this is called 7-point stencil, but then you can get like, I don't know, like arbitrary numbers. But this is still a useful example. Okay, so if you did this within a block, using the same block example that we had, each thread does one output element. And we have blockdim.x elements per block, so we have multiple blocks. And your input elements, but the difference between this and vector-wise add is that now you have reuse of elements, like multiple output elements are going to share the same input elements. So with radius 3, every input element is read 7 times. So suppose that we're computing this thing, or yeah, we're computing this thing in the output, and just like using this as an example, so how many times are we going to pass over it? We're going to pass over it 7 times, like as we shift down 1, 2, 3, 4, 5, 6, 7. And then that's it. And that computed 7 elements in your output, but you had to keep reading this element. So that is different from vector add, because vector add, like everything is just touched once, but in Stencil, you have many more reads from your input than writes to your output. And yeah, so like I said, GPUs have also a memory hierarchy like CPUs, but it's different because in CPUs, every level of the memory hierarchy is implicit. Like you don't have to manage any of it. It's like L1, L2, L3, but everything is managed by the hardware. In GPUs, it's not true that everything is managed for you. Global memory is managed for you, but shared memory is not. So you can think of shared memory as just like an array that you have access to that you can manage however you want. Like you can put whatever data into it that you want and you can access it faster within a block. So that's why you use threads, because you can access the shared memory. And yeah, it's user managed and it's not, you can't access it between blocks, and it's usually on the order of kilobytes. It's not huge, but it's not super tiny. And global memory is in DRAM, which is a farther memory, and this is what you get when you have CUDA malloc. So this is shared across the threads, and usually this is on the order of gigabytes. So you can technically do communication between the blocks if you use global memory, but it's much faster to do it in shared memory. Okay, so if you wanted to implement this stencil in shared memory, you would first read this. This is your length of your block, blockdim times plus your radius element on both ends. This is the number of input elements that you need from your global memory into your shared memory to do the computation if you want to compute blockdim.x output elements. And yeah, so you compute this many output elements, and then you're going to write this many elements into global memory, and you have slightly more input elements than output elements, just 6. So this is how you would use shared memory in your stencil kernel. So this is again like your global to specify the function. The stencil 1D is void because you're going to write the output into an array, and you specify it using shared, like here. And this is just the rest of it just looks like a C stack allocation. Like you specify how big you want it, and it goes into shared memory with this keyword. And then this is your global index, like we calculated before. Block index times block dim plus thread index. And yeah. And then this is your thread index plus radius. Oh, okay. So this is what you're going to read into shared memory in the beginning. Because so if you run this block index, or if you run this thread index number of times where each thread index is separate, then you just copy in these values. And so you need to fill in these on either side, and that's what this is. So not all of the threads, this is the number of threads you have, not all of the threads need to copy these endpoints, only the last radius, only up the first radius do, and then you just copy in the front and the back. Make sense? Okay, and then after that, you would apply the stencil. So every thread computes this. Every thread has some index, and you're going to do, this is just the radius, like the distance around you. You have your global index. You are computing negative radius and positive radius around you, and then you accumulate that into the output. This is some temporary result, and then the output at the global index is just going to get the result of this 7-point summation. There is some issue with this, which is that this previous code doesn't work exactly because the threads are not guaranteed to execute in any specific order. So the issue is that some threads, basically like the first step was to copy the memory. And then the second step is to compute the stencil, but you need all the memory to be copied before you compute the stencil. And if some threads are faster than others, then you're not guaranteed that the memory is there before you start to do the stencil in some other threads. So some threads can run ahead of the others, like here, if you're trying to compute this output, you need all of these 7 points. But if, for example, this thread was much slower than this one, this element is not guaranteed to be there by the time you do this summation of these 7 points. And so that is not totally correct. But you can do synchronization, so you can call
Is
synchronous.
that like, so like that input, is that like the original like post to device copy that might happen, or is that like for a different copy that happened in the previous method?
That was the shared memory copy. So let me go back a little bit. Yeah, so originally we did some hosted device copy for input,
Yeah,
and now we're trying to copy the memory from input into shared or into temp.
Yeah.
And so if you're just temp is like this assignment, and this is filling in this part, and then this part is filling in these two ends. So if like a different thread was past this point and you're not done with this for some earlier threads, then you may not get all the data necessary. Does it make sense, like what the issues?
So we, like, in summary, we had it basically copied from host to device DRAM, and then from DRAM to static SRAM or the shared memory.
Mhm.
And then from there to synchronize barrier or whatever,
Mhm.
and then afterwards do the compute.
Yes.
So is there any way that you don't have to load all this data through DRAM? Like you can, you know, that you're gonna just send it over to SRAM, so why, is there like a method to bypass that and just ignore writing to DRAM?
No, I think you need to, everything needs to go through global memory in the GPU. Just like in the regular memory hierarchy, like on CPU, everything needs to go through DRAM. I think you have to go through the levels.
Why do we have to do this shared memory again? Because like, when let's say the first radius, 2 times radius plus 1 elements are loaded.
Mhm.
The next time the thread actually starts, when the next thread starts reading it, the first 5 elements are common. But like the first few elements are common anyway.
Sorry.
So,
So the question is, why do you need shared memory? Because you have common elements?
yeah, like, I mean, it's anyway loading them into like the higher level of RAM. It's already loading them into shared RAM when it's doing its computation. Like,
It's not. There's no, shared memory is explicitly managed by the user. It's not like the CPU where like everything would automatically get loaded into L1 if you access it from DRAM. There's no caching unless you do it explicitly in shared memory.
oh, so by default, it just reads everything from DRAM.
So like if you didn't have this, then you would have to keep reading like the shared elements from DRAM.
So are other variables are stored in register, for example, G-index?
Yeah. Yeah, like G index and L index and stuff. Yeah, GPU threads have registers also.
But if we have too many this kind of variables, what would
It would have to do, like if you had more local variables than registers.
Yes, so my question is, where do we store these variables? To global memory or?
Probably to global, like, if you run out of registers, it probably can recompute. Like, if it can recompute the things, then it just needs to store the minimum number. Like for G index and so on, if you, like you can compute them through global variables, which you always have. And I guess those are also stored in registers. So if you can recompute them from the global variables, and there are too many of them to store in the registers, you can just keep recomputing them and like do some like register reuse. If you have too many and you can't recompute them, then they would probably go to DRAM. Yeah. So that is stencil, and the only reason that you would use shared memory is if you, I guess only it's the same as in CPU. Like the only reason that you use caches if you have reuse. For vector add, there's no reuse. Everything was just touched once, so it doesn't matter if it was in DRAM. But if you ever have to access something more than once, then you can consider loading it into shared memory. So going back to this, the issue is that the threads are not guaranteed to run in lockstep. And so if all the threads have to do the copy first, and then they have to do and they have to write. So you need to make sure that you have all the data loaded in your input before you can compute the output. And that is why you would call synchronization. So you can call sync threads, which synchronizes all the threads within the block. Yeah, and this is just the barrier. You have to if you reach the barrier, you have to wait at the barrier until everybody has reached the barrier, and then everybody else can continue.
Another question about the previous one, like you could point about the registers, like,
Mhm.
I think for CPU, you don't have to worry about it as much if something is not loaded to register because it's put into L1 or something close by from cache. But here in this case, like to fix that, one way I can think of is like explicitly putting everything in shared memory, which sure is fine, but that means everything has to be there, like all your variables, and
Mhm.
you can't say like, okay, variable A or variable B will sit in there unless you do like some other intrinsic stuff that we had before, like loading into the GPU registers. So like, is there, I guess, some better way of managing, like working with both the registers and shared memory? So that way we don't have, while like also maintaining a code quality. So that way we don't keep going between registers and gold memory and back and forth, which I'm sure is really costly.
So like, maybe let's go back here. Like for these examples, you only use these once. So it doesn't really matter where you store it, because like even if they were in DRAM, you would only need to access them once. I don't know of a better way to do it. Like if you really do need to reuse your variable, I don't know of a better way than to keep it in shared memory. Maybe like if you could pre-compute it, like outside of the function, then maybe you could pre-compute and just pass it in, and then you wouldn't have to keep redoing the work to remake it. But don't know of that many cases where you have something like this that is used more than like a couple of times. Usually
You have like registers per block.
there are registers per block, and there's also registers, I guess like there's registers per thread, which turns into registers per block
Oh.
because there's threads are organized into blocks. Yeah, you can think of the blocks as like the threads are finer grained than in CPU, and the blocks are more like what we would call cores in CPU.
Yeah.
Like the threads are like
Is that
tinier.
software or hardware?
This is so you specify like a number of threads, and then there's some scheduler that maps them down into the hardware threads. But the GPU hardware threads are like lighter weight than the CPU threads. CPU
Oh,
hardware
so they're
threads.
Virtually like it's still be values in threads register. And then they'll be loaded once the thread is spawned back into
Mhm. Yeah, like yeah, the thread it's like a different paradigm than on CPU. Like you want like more finer grained parallelism in some sense. And like we specify the number of threads per block in the run configuration, but like that's not the number of threads per blocks in hardware is fixed. So there needs to be some mapping from what you wrote into what is actually there.
Well, one more question, actually, how many threads are there per block is hardware threads?
It depends on the GPU.
Like an A1.
I'll go through a couple of examples. Okay. Going, like you said, for this thing, you just call sync threads after you copy the data, and then you keep going, and then you compute the end of your stencil. I didn't even write it because it's the same. Okay. That's it. All right, so this is an example. This is kind of an older GPU. Maybe this will answer your question. So the way that GPUs work is that like the basic building blocks on a GPU is called shared multiprocessor, or SMs. And at a very high level, the way that you can think of SMs is like, SMs are like, they're kind of like sockets in some sense on a CPU. Like they have some number of threads and they have some number of blocks. And to scale up your GPU, you can just like kind of, from a hardware sense, like you just copy your SM repeatedly. And so, yeah, so the cores per SM are fixed, and then they have some specification. So this is an older one. The cores on one SM, there's 192, this is single precision, 64 double precision. And then they have load store units, and then they have 64K registers. Yeah, you have some schedulers. I will explain what a warp is later. every warp scheduler is dual issue capable, which means that you can issue 2 instructions at once. You can do 1 single precision and 1 double precision in every cycle. And this is like an order of what they used. This is like an older GPU, so they're smaller. Like you can see, this is 5 GB, 612. These are pretty small. And these have 13, 14, 15 SMs. So like as they got more advanced, then they just got more SMs. And this is like the number, this is like the number of threads per SM. So you're asking like, what is sort of the order of magnitude that you would see? This is what it used to be like. And then now, this is more recent. So this is like a Volta, which I guess like V100. So now you have 64 single precision, 32 double precision, and this is just the clock rate. And you have 56 SMs. So this would be 56 times 64 and 80. This is V100, 80 times 64. That's kind of what they look like. They got a little bigger. Now this is 16 or 32. They're still not huge. Like this is still much smaller than CPU DRAM. And then also there's this fancier thing that they introduced called Tensor Core, which I guess is like their marketing name for it. But it's basically like an accelerator for small matrix multiplies.
You explain the term warp.
Yes, I will explain it in like 2 slides. Thank you. If I don't explain it, if you still have questions, then you can ask again. Thanks. Okay. Yeah, so you're asking like, what is the mapping from software to hardware in GPUs? So there's software threads in GPUs, and each of those is like 1 scalar processor. So that was like the single precision or double precision unit from before. And we have thread blocks that you can specify, and those map onto multiprocessors, like basically mapping onto SM. And then you can have a grid, and that's for the grid is blocks times threads, and then that maps onto the entire device. So yeah, the threads are executed each by the scalar processors, and then overall you would execute the entire thing on the device. And depending on the scheduler, like the software thread blocks do not necessarily need to have a 1-to-1 mapping with the hardware multiprocessors. Like you can have multiple software thread blocks on one hardware multiprocessor. Okay, so a warp is this hardware, it's like the minimum hardware unit on a GPU. It consists of 32 hardware threads. And if you concatenate if you like put together a bunch of warps, then you would make 1 multiprocessor. And the minimum number is, yeah, the number is 32. And the warp is executed in SIMD fashion on the multiprocessor. And actually, like threads do not operate independently. The minimum number of things that you can launch is a warp. Does that answer your question? Yeah. Mm-hmm. Yeah, so on the GPU, instructions are issued in order. So this is separate from CPU. On CPU, actually, I think I didn't really talk about this, but you write your straight line code in CPU, and then it gets compiled down to assembly. The underlying thing can actually reorder those assembly instructions subject to some constraints if it thinks that it will be faster. But the GPU doesn't do that. Everything just executes in order. And yeah, and the way it works is that you have to normally, like in your program, you would load the memory, and the thread would wait if your operand isn't ready. And this is similar. So similar to in CPU, there's also this issue of memory latency. Like everything kind of goes back to memory latency because it's always way slower than compute. And GPUs are latency hiding, which means that they have these multiple threads and they hide their latency by switching the thread if somebody is stalled. And from global memory, the latency is like over 100 cycles, and the arithmetic latency, which is like how long it takes you to do an operation, is usually less than 100 cycles. So it is faster to do math than to load, just like everywhere else. And yeah, so this is, so one question is like how, like I was saying, like as a heuristic, you want to run on the order of 256 or maybe 512 threads per block. And how many should you launch? And the reason that you want to launch as many threads as possible is for latency hiding. So this is your code. This is what we had before. This is vector add C is A plus B. And in machine code, this becomes load A, load B, and then multiply A and B to get you something into R2, which you're going to write into C. Okay, so this is how it would work. So this is your machine code. And then you have some number of clock cycles. So this is just like time. going from left to right is forward in time, and warps. So you have this number of warps and pretend you have some more, but this is how much I can illustrate. And so like you're running your program and you first see, because it's in order, you first need to load R0. So you're going to load R0. And so instruction 0 needs to get issued before instruction 1. So you so you issue instruction 1. And here we're just going to schedule it. Like the scheduler is just going to put it on warp 0. It doesn't actually matter what warp you put it on, but just for now, you can put it on warp 0. And because there's latency, now you have to wait because this is a load and load takes a while. Okay, so I0 is issued, and now you can issue I1 while you're waiting for the first load to finish. So both I0 and I1 are in flight, so you're waiting for the load. But now you have this issue because both are waiting and you can't do this multiply until you get both. So what the scheduler will do is that for a different thread or for a different warp, it will issue I0 for a different element. And so now you go to another warp and you issue this one, and then you have the same issue. So you run into latency again. And then you basically keep going, like you fill your entire pipeline using these load instructions. And you keep issuing them in other warps. And then eventually latency will end. Eventually you get your data, and now you can issue I2. So you can multiply the data that you got. And you can imagine, basically the intuition is like, if you had an infinite number of warps or infinite number of threads, latency would kind of like never be an issue, because eventually you would come back around and your thing would get loaded. And then in the next instruction after this, now like, because it's pipeline, like now this would get satisfied, and then you can issue I3 for that. And then like all the way down that way. Oh, sorry.
So,
Reverse
I'm
transfer.
wondering how does the work of that, all of the instructions. Because, you said we can launch I0 and I1 together.
You can launch I1 after I0. But you're saying, is the question like, how would you know that I2 can finish? How do you know that you can do I2 now? Like there's some notification when the latency gets satisfied.
There are two types of instructions. One memory,
Yeah.
IO, and memory.
Yes.
Whenever we have a we have to check if our previous IO cloud method finished.
It's not like the compute command doesn't, like, for example, like here, this multiply, there's no checking if this is finished. There's like this, you cannot, like the scheduler cannot issue the next one until this has finished. The scheduler needs to know somehow, based on latency, that both R1 and R2, R0, R1 got loaded.
And how can scheduler launch I1?
Because I1 has no dependency on I0. I1 is just like loading B.
So suppose we have suppose I2 doesn't have dependency with I0 and I1, just that random compute. It still needs to wait.
No.
No.
It could keep going. It only has to wait now because it depends on the results of loading the data. But if it like did some other random stuff, I2 could just proceed.
How many of those kind of independent instructions can you issue to one fork? It's just the number of threads there,
How many independent instructions? Yeah, they're dual issue. So if you have one single precision, one double precision, you can issue as many as warps you have. Pretty much. Or sorry, you can issue as many math instructions as threads that you have given one warp.
One scheduler just launch the commands in different warps in the same cycle, because I can't see any dependency between warps.
I see, like why can't you load more data? You have some limited load store ports on the GPU.
Because bandwidth.
Yeah. And so you can only satisfy like in this example, you have load store ports equal to number of warps. Good. Yeah, so, oh, sorry, let's go back.
You said you can't load the I0, I1 and W1 because of bandwidth. But then if that is, I mean, that's the reason I2 is being blocked, right? Because that particular bandwidth is being utilized. So how could you start the next one? Like, how can you start a new one?
How can you, because you can issue them. Like there is some time between issuing the instruction and actually getting the data. So like bandwidth is in some sense, like once you reach the steady state of loading your data, like how many bytes can you load per second or gigabits or something. But there is some like startup cost. There's like some minimum latency is like how long does it take you to load 1 byte, no matter how many bytes you're loading. And so you always have to incur latency cost, like when you first start. But once you fill this pipeline, you're running at like bandwidth speed. Does that make sense? You can issue 2 math commands in each cycle. 1 single precision, 1 double precision.
So if we can do that, why can't we do both I0 and I1 in one clock cycle?
Because these are load instructions.
Oh, those are not.
So yeah, so this is how the GPU does latency hiding. And to get good performance, you want to saturate the number of threads. So you want to spawn as many threads as possible to keep the machine busy while you have to deal with latency. So you can keep issuing instructions as fast as possible. This is just a plot. So the x-axis is number of threads per multiprocessor. Y-axis is how much bandwidth have you reached, and the theoretical max that you can get is 120. And this is just showing that if you access more contiguous bits, like this is 128 and this is green, then you can reach peak bandwidth faster. And that's kind of the same as it was on CPU. Like you want to access contiguous memory as much as possible. And yeah, so that depends on your data and how you stored it and your access pattern. Yeah, so you need as many threads as possible to keep your GPU busy. Ideally, you want 5 threads or 512 threads at least per SM. Aim for 2048, but 512 is usually fine. And you want more threads if you're doing one math operation per thread, because you can do, ideally you can issue 2. So like 1 thread can issue 2 instructions per cycle, but if you're only doing 1 instruction per cycle, then you need to like double the number of threads to match. Yeah. And so how do you determine the thread blocks, like threads per block versus number of blocks? The thread per block should be a multiple of the warp size, because if it is not, then you still have to spawn the warp, but then you're just wasting the threads at the end of the warp, because the minimum multiple of like anything you can do on the GPU is 32. And the SM can execute at least 16 thread blocks. On more advanced ones, you can actually do up to 32. And there's this trade-off. So if you have really small thread blocks, you don't have good occupancy, which is thread usage. But if you have large thread blocks, then they're less flexible, because like everybody has to be doing the same thing. And generally, a 128 to 256 threads per block is totally fine for most applications, but it depends. But 256 is safe. And occupancy is the measure of the thread load in the SM. So that's peak theoretical usage versus peak achievable usage. And then there's this occupancy calculator spreadsheet that CUDA provides you. And it takes in things like registers per thread, threads per thread block, and shared memory usage. And it uses those to calculate the occupancy that your application achieves. Okay. So to wrap up, GPUs get efficiency from simpler cores. Like the threads on the GPU are way simpler than CPU cores, and they have less overhead. So like the high level GPU design, like CPU has a lot of other stuff like control logic, which GPU doesn't have. And yeah, so then you can, like the threads are smaller, and then you can optimize more for parallelism because they're more lightweight. In heterogeneous programming, the way it works is that you have the host and the device, and you need to manually offload your code from the host onto the device. And in this example, the device is the GPU. And for GPU, you basically need to optimize for data parallelism. So one of the main things that people optimize on GPU is like prefix sum, because prefix sum is like a classical data parallel algorithms. And it's not as strict as CPU SIMD. Like in CPU SIMD, everybody needs to do the same like plus or minus or whatever it is. But on GPU, like you can technically have branching within your threads. Yeah, this is the CUDA documentation, and there's more links. Sorry. Are there questions?
If you go back to the, like, the chart, not the chart, but like the graphic that you made with the warps and then the, yeah,
This thing.
so, okay. I was confused between you said, or they're not understanding something, but like, can we just not issue like all, or not all, but like a bunch of instructions for each different index, like at the start? Or are we doing that, or is this like only one core and?
Why can you not? Oh, okay, I see. So why can you not put like all of I0 here and I1 like
Yeah.
just vertically? Because you have limited load store ports on one SM. So this would be like, in this example, this would fill up the load store ports for one SM, and then that's why you would have to issue them. This is like pipelining the load stores basically across the warps.
Oh, I guess like. Is it like, okay, so like, wait, but, okay, so you're using that load store ports, but then you're issuing all of those while that's still like happening, right? So, or maybe I'm,
Yeah, I think somebody else asked this too. So like, aren't the load store ports busy until we have loaded, like what's gonna be loaded to R0 and how can we see them?
So you can issue the instruction and the load store ports are not busy until they're receiving the data. So you can,
so-
like in the next step after this I2, you could do I2 here. Because then like these I1, I guess in the next two next steps, but
okay,
this
so
one would, like, you don't have to wait another latency length for these to finish.
the load store ports are just busy while you're issuing the instructions. And
Then
they're
they
busy
just
when
kind
you're
of.
getting- And they're like
Yeah.
fine, and they're busy when you're getting the.
Yeah.
So, okay, so that's why you, okay.
Still that question. So, how about the scheduler know that, I2, registers I2 needs are filled in I0 and I1. How that?
Like here, you mean?
Yeah.
Like-
My question is, how can scheduler track the dependency?
How can scheduler detect the dependency between instructions? Like it can build like a graph on the registers, basically. Like here I2 uses R0 and R1, and it can see that R0 and R1 happen in I0 and I1. The scheduler, it is implemented in software. But yeah, the scheduler is like a mapping between these instructions and onto the hardware warps.
Okay, that's another thing. How is this different from it just being, single threaded? Cause like,
How is
single
different?
threaded, wouldn't it just be like you're issuing, or not, okay, maybe not single threaded, cause like obviously the multiply thing, but like. Is it, okay, so. I guess like, maybe I wasn't exactly paying attention, but like the warps, do those correspond to like threads, or is that a different thing?
Warps are 32 hardware threads.
Okay, so in that case. You're still only like using one thread at a time, right? In this case?
Yeah,
It's like you're waiting on it, and so that like it assuages some things, but. Like in a normal like CPU architecture, like let's say you ran this code.
Mhm.
What would like, would presumably the same thing happen, or would it be like different, even if you have like one thread in like a CPU? Would it be able to like not like execute, if it was in a for loop, would it be able to execute like a bunch of those loads before it did the multiply, or would it still wait? Or that,
so you're saying like on a CPU, could you load like other data while you're waiting for the multiply?
Yeah.
Yeah, you can issue more loads into the pipeline on CPU also.
Okay, and then. So. What am I trying? For, in like, okay. Yes, the warps are hardware threads, and so. Could you like. In a single warp. Like, let's say like you only had like 2 warps for the sake of argument, and you had this loop for like. Or not this loop, but you had some doing that or some other task. Let's say like you, and so you had saturated this thing where they're both waiting for latency.
Mhm.
On latency, could you do like more computation on that? Like,
Yeah, you could do like other separate computation.
okay, so is like warp 0 from C0 to C13 available to do like other things if. Like, if like the schedule like gave it to it?
I'm sorry.
Like, so warp 0 between like 2 and 13 would be able to do like other computations.
Oh. Not on warp 0 because the GPU is in order. Which means that it has to finish the instruction. It has to finish, well, actually, no, maybe, because like it can issue I1 before I0 is satisfied. So like you could do other math in here, I
Yeah,
guess.
like, yeah, could you do like other math, like if,
Yeah.
cause like then, cause in that, in this case, or in that case, then like. The warps could be like, the threads could be utilized even when it's waiting for like IO to finish.
Mhm.
Okay,
Yeah.
so it can do that.
Yeah.
Okay,
So all the warps here are for a single SM.
Yes. In this, yeah, in this example, it would all be for one SM. But you could like, if your problem was big, this is just like vector add. So like if your vector was huge, you could run on more than one SM.
Yeah, but
And each SM would be doing this pretty much.
Yeah, but then this, the same thing would repeat over all the SMs.
Yeah, every SM would be doing this pipelining.
But then like so like, let's say that like n number of SMs, so there are n I0, I1s going parallel.
Just to recap again, I just want to get a high level summary. So the warps contain the hardware threads that are implementation in C or CP or CUDA is that the blocks and the threads are software abstractions.
Mhm.
So a block can technically contain like 1.5 or something warps, basically.
Yeah, you can specify threads per block to be any number, but you should specify to be a multiple of 32.
Yeah. So that way,
That way, because you cannot launch more than a chunk of 32 hardware threads.
and then the shared memory, that's something that's, I actually forgot. So is that shared among all the warps? Is it a curved one?
That is shared among all the warps in one hardware thread block. Or in one software thread block.
Oh, I see. So this is soft, okay. I see.
Yeah, like there's like, the angle brackets, like number of blocks and then threads per block. So the threads per block can share the shared memory.
So in reality, though, in the hardware, there's just there's like a big massive amount of SRAM sitting there, but software divided up for each of the thread blocks to handle.
Mhm.
So threads within this block handle that. from the
Yes.
software perspective.
Yes.
A very simple question is, why does it have to load the same register multiple times across the different block size?
Oh, okay, because like here's just one example of like doing one addition, but actually you would have many of these, like your problem is of size n. And so you would need, this thing would be copied, like every thread needs to do this, and you would have a lot of these.
So just trying to understand like the memory hierarchies a little bit more. Well, when you're like buying a GPU, it always says like VRAM. Is that like the DRAM?
Maybe? Is VRAM like their marketing name for DRAM?
Like VRAM?
Mm,
In any case, and then like the
Maybe.
SRAM is like so marginally smaller, right? Like you're saying there's only like orders of kilobytes for like the entire GPU of SRAM?
yeah, of shared memory,
I see.
whereas like the whole thing would be gigabytes.
That makes sense.
Yeah, actually, I'm not sure about VRAM. Let me check if it is the same as DRAM.
associated program is just like portion of that RAM that's like dedicated to just the graphic cluster.
Oh, that makes sense, because sometimes like on GPU, they have like separate caches also, like for different applications. So like, I guess one of them is for video.
How different is GPU DRAM from CPU DRAM?
How different is it? Um, I think similar, like from a software perspective, like it acts the same. You can just access stuff in it. I think the main difference is like that you have to manually manage the hierarchy.
So the reason for threads and blocks is that threads can be synchronized and shared memory. But then like you said, those three dimensions, block index X, Y, and Z.
Mhm.
So is there some sort of sharing there also? Or what is the reason for the X, Y, and Z?
Oh, the X, Y, and Z is just to easily, like, more easily express 2D or 3D computations. Like, you could express everything in 1D. Like, if you have like a 1D array of threads, you could do like matrix computation and you just cut it up yourself into rows.
Because like you do a times logged in dot X.
Mhm.
So that means like take thread, that's like using contiguous memory in some sense. So is the hardware also abstracted in like an XYZ pattern so that you can also, like the shared memory also being abstracted in like an XYZ pattern, so memory.
I think the XYZ thing is just a software level thing. Like in the hardware, you just have like your SMs and your warps, and those are pretty much in 1D. The 2D is just for easier expression of 2D algorithms. Yeah. Oh, that's pretty much time. Thank you.